Hey everyone, and welcome to today's Explainer. This one is brought to you by Forge College. Now, if you've been following along with our Applied Solidity development track, you know we just wrapped up our lesson on drafting documentation, processes, and runbooks. And yeah, I know, it was a bit theoretical, maybe a little heavy on the paperwork, but absolutely necessary. Still, let's be real here. We're all itching to actually get our hands dirty again and build. So today, we're moving past the runbooks and diving headfirst into the highly anticipated capstone assembly of our integrated smart wallet project. We're going to take all those isolated pieces, the components, the audit outcomes, the test suites, and we're synthesizing them into a fully functional, totally deployment-ready smart wallet. So let's just jump right in. Here's a quick look at our blueprint for this final hangar inspection. We'll start with the acceptance criteria, move into build, implement, and test. Then we'll wire up the integration hooks, hit the final checkpoint, and finally, package it all up for deployment.
Okay, Section 1, the acceptance criteria, or defining our pass and fail gates. Look, deploying an unaudited, untested smart wallet to mainnet, that's basically like leaving your front door wide open, heading out on a month-long vacation, and hanging a giant flashing neon sign on your porch that says free ETH. I mean, it's just a spectacularly bad idea. To stop us from doing something that catastrophic, we rely on objective deterministic rules that definitively tell us when our code is actually safe to ship. We've got 4 non-negotiable structural integrity gates here. First up, your core unit and integration test suites, they have to run and pass with absolutely zero failing tests. None. Second, our coverage metrics need to hit a minimum 80% threshold. That means at least 80% of our code lines or functions are actively being exercised by our tests. Third, every single high-priority audit issue we found earlier must be completely resolved in the code or at the very least, strictly mitigated with solid documentation. And fourth, our integration hooks have to be fully documented and tested so that external systems can actually interact with our wallet safely. Listen, if even one of these gates fails, the milestone just isn't complete. Period.
Moving right along to Section 2, build, implement, and test. Welcome to the assembly line.
All right, so this is where the magic happens. We pull our audit remediation branches from those earlier security reviews, merge them right into our working tree, and send the entire code base through a totally relentless automated gauntlet. It's a strict sequential execution. Every single step has to execute perfectly before you're allowed to move on to the next. Step 1. You compile locally without a single error using your project-specific compiler. Step 2. Run those core and integration test suites until you are looking at exactly 0 failures. Step 3. Generate your HTML and JSON coverage reports. Step 4. This is where we execute fuzzing invariants and property tests to hunt down any of those weird edge cases. And finally, Step 5. Profile your gas consumption on critical flows, things like deployments and token transfers. And hey, a quick pro tip: you really want to automate as much of this as humanly possible in your CI pipeline. Humans shouldn't be the ones manually verifying a build. We make mistakes. Machines don't.
Now, when you're profiling that gas consumption, keep your eyes glued to this specific threshold, 15%. If you see any gas regression over 15% compared to your previously established baseline, well, drop everything. That needs immediate attention. You've got 2 choices here. You either write up a really rock-solid engineering justification for why this shiny new security feature or abstraction is somehow worth the massive spike in transaction costs, or you roll up your sleeves, get back into the code, and optimize it. Because in the world of smart contracts, gas is literally money. A blooded contract is a dead contract. Simple as that.
Okay, Section 3. Wiring the integration hooks, also known as connecting the docking bay. I want you to think of this phase as building a highly secure docking bay. Because sure, a smart wallet on its own is great and all, but its true power, that comes from interacting with the broader decentralized ecosystem. Which brings us to a really critical architectural question. How exactly will our isolated, heavily secured wallet securely talk to something like a future token sale mechanism? Seriously, think about it for a second. Our wallet's entire job is to abstract away complexity and aggressively protect the user's state. So if an external token sale controller suddenly needs to, say, enforce a purchase cap or whitelist a specific buyer, how do we let it do that without completely shattering our wallet's internal security abstraction?
Well, the answer lies in what we call an integration hook. These are your developer-facing interfaces, explicit events, and adapter contracts. Basically, they act as a highly secure API for your smart contract. Instead of letting some external protocol just reach its hands directly into your wallet's core logic, which, by the way, is incredibly, terrifyingly dangerous, you provide these explicit hooks.
These hooks are what allow a token sale contract, for instance, to safely register wallet ownership for a whitelist or execute off-chain indexing, all because your hooks are emitting explicit trackable events. To put this into practice, you need a very clean, clearly designated entry point. Take a look at this code snippet. By declaring a function like execute sale, we're basically giving a token sale controller permission to initiate a transfer or a credit within our wallet's abstraction. We're not just crossing our fingers and assuming a standard ERC20 transfer is going to magically play nice with our custom architecture. You provide this Solidity interface, and ideally, a solid JavaScript example to go with it, so that external developers know exactly how to integrate with your creation safely and securely.
Let's move on to Section 4, the final checkpoint, executing deterministic verification.
A huge part of this checkpoint revolves around the audit remediation report. And honestly, this forces a pretty vital engineering reality check. Because your subjective feelings about how pretty your code is, they don't matter here. An external auditor or a reviewer has to be able to run deterministic commands to definitively prove, beyond a shadow of a doubt, that the wallet is deployment ready. Now, an unresolved high-priority finding, that is an absolute non-negotiable launch blocker. Stop right there. However, a documented mitigation with compensating checks and a clear timeline, that is an acceptable reality. Look, sometimes in the real world, you just can't perfectly rewrite a core function without breaking literally everything else in the process. In those specific cases, a documented, thoroughly tested mitigation where the risk is actively accepted, understood, and tracked is how we move forward. Just remember, you absolutely must have a paper trail for every single audit ticket.
And when that reviewer runs your test suite locally, this is exactly what the verifiable JSON output should look like. Tests 124. Failures 0. There is zero room for ambiguity here. None. If a reviewer runs npm test or forge test and sees even a single failure, or if they notice your coverage report dipped to 79%, the milestone fails. Period. You go right back to the code. At this stage, machine verifiable evidence is the only evidence that actually counts.
Which brings us to our final section, Section 5, Packaging for Deployment. Time to load the payload. All right, assuming all our lights are green and our JSON output is looking absolutely flawless, it is time to safely box up our verified code for the staging networks. But to do this right, your repository needs to be impeccably organized. It's like a giant puzzle where every piece has a very specific home. Your compiled ABI and bytecode, those go straight into your artifacts folder for the consumers and deploy scripts. Your HTML coverage evidence heads over to the reports folder for the assessors. All that documentation of fixes gets filed in the audit folder, and your shiny new token sale hooks guide goes right into the integration docs. Keeping your naming consistent like this makes automated assessment an absolute breeze, and it ensures that nothing gets lost in the handoff.
Okay, I need to pause here for a very firm and frankly slightly painful reminder. Please listen to me on this. Never, ever, under any circumstances, embed your private keys or your RPC endpoints directly into your deploy scripts. I mean it. Hard-coding your private keys into a JavaScript file and pushing it to a public repo is a fantastically efficient way to instantly donate every last drop of your project's funds to MEV bots. Seriously, they will drain your wallets before your GitHub page even refreshes. It's brutal. Always, always use CI-safe environment variables for your deployment configurations. Keep your secrets secret, folks.
So, if you followed this entire capstone process, the compiling, the testing, the mitigating, and the clean packaging, congratulations. You now have a fully auditable, deployment-ready smart wallet. And trust me, you're going to need it, because in our next explainer, we are jumping right into Introduction to Token Sales and ICOs, where we will actually put those integration hooks we just built to the test. I want to give a huge thank you for joining me on this deep dive today on behalf of Forge College. Remember, mastering these complex architectural patterns is exactly what separates average coders from truly elite Web3 engineers. If you want to learn more about this subject, access our full project repositories, and explore a ton of other Web3-related topics, make sure to visit our website at forge.college. So as you stare down your final deployment script today, I want to leave you with this. If $1 million flowed through your hooks tomorrow, would your architecture hold the line, or would it completely shatter? Think about it. See you in the next explainer.